Bigger, brighter, more massive. The early galaxies that the James Webb Telescope has detected in the depths of space pose serious problems for experts. In detail, such large galaxies are unlikely to have existed so soon after the Big Bang. But that's not all. When Webb carried out some observations on the puzzling deviation of the Hubble constant, it confirmed that the rate of expansion of the cosmos is actually much higher than it should be. But how can this mysterious discrepancy be explained? Well, quite simply by the fact that our universe is just one of many, and that the cosmic worlds are in the process of merging. What at first sounds like the idea of a creative science fiction author is actually the hypothesis of an official research study. A research study whose results are more consistent with observations in space than the standard cosmological model. No James Webb telescope will help. No matter how powerful a space telescope we send into space, we will never be able to see beyond the edge of the observable universe. In view of the fact that the universe is isotropic, or in other words, it always presents itself to the observer in the same way, regardless of the direction of observation, there is a spherical space around our Earth that defines our cosmic field of vision. The fact that our view of the stars is limited is in turn due to the expansion of the universe. However, the cosmos is not expanding into an existing space. No, it is rather the space itself that is constantly getting bigger. As a result, we cannot determine the distance to the observation horizon by simply multiplying the age of the universe by the speed of light. This is because, taking cosmic expansion into account, the distance is not 13.8, but 46.3 billion light-years. And in fact, the distant structures that mark our visual barrier today were just 40 million light-years away from us at the time they emitted their light. However, as the light that is currently emitted from there simply can no longer reach us, we know neither what processes are currently underway there, nor what lies beyond the observable universe. What we do know, well, skeptics would say we think we know, is how the universe began 13.8 billion years ago. According to this, everything began with an unimaginably hot, dense point, the so-called singularity. From this proverbial primordial seed of everything, space, time, and matter eventually emerged together, and the cosmos began to expand, and by no means at a leisurely pace, but as part of an explosive expansion known as cosmological inflation, which lasted only a tiny fraction of a second. In detail, the universe expanded by a factor of 10 to 26 in this absurdly short time. In other words, it became 100 quadrillion times larger than it was before in the blink of an eye. So far, so generally accepted. But in the same breath, cosmological inflation also raises at least two central questions. Why did the cosmos start expanding exponentially fast in the first place? And why did it subsequently stop? Is our universe just one of many? Well, in simplified terms, experts assume that there was or is a special field that has had a significant influence on cosmological inflation, the so-called inflaton field. Depending on the state, this can cause the cosmos to expand, and not just expand, but expand absurdly fast. And in the event that the inflaton field was in a false vacuum shortly after the Big Bang, random quantum fluctuations, or in other words, tiny, random fluctuations in the values of the elementary particle fields, could have caused it to switch to a real vacuum or another false vacuum with lower energy. For a better understanding, a true vacuum in this context means a region with minimal energy, which does not necessarily have to be zero. In fact, a true vacuum can very well contain mass and energy. There just cannot be a state in which this area contains even less energy, because then it would be a false vacuum. Applied to the theory of inflation, this means that the change of state in the inflaton field has triggered the exponential growth of the universe. However, during the transition from one vacuum state to another, the field also emitted energy in the form of radiation and matter. This is important. After all, the matter that was now present in the cosmos slowed down and ended the inflationary expansion phase so that the universe could then expand at a normal rate. However, there are also researchers who have their problems with this common assumption, and by no means just since yesterday. The American physicists Paul Steinhardt and Alexander Vilenkin already put forward the theory in the 1980s that cosmic inflation has not in fact come to a complete standstill. Put simply, the random quantum fluctuations could lead to the formation of individual bubbles in which the inflatant field takes on just the right value to end the inflation. Elsewhere, however, and this is the crucial point, cosmic inflation could continue unchecked. In other words, what we commonly refer to as the universe is actually just a bubble-shaped sub-region in which our world has been able to unfold. Conversely, however, this theory also goes hand in hand with another compelling insight. Because if this is really the case, there must also be other bubbles in which other universes have formed. In this context, the Big Bang would therefore by no means be the beginning of everything, but merely the start of the inflationary stop in our cosmic bubble. In fact, in this scenario, there is no such thing as a beginning of everything at all, only eternal inflation, from which new universe bubbles are constantly spitting out. Of new theories and colliding baby universes. There is no question that the conclusions derived from the cosmic bubble model are extremely exciting. But assuming that it really does correspond to reality, is there a way to somehow observe the other universes or even make contact with them? Well, the majority of scientists answer this with a definite no. Because we are inaccessibly separated from the other universes by the inflationary expansion of space. However, it should be noted at this point that not every expert is convinced of this inaccessibility of worlds. Quite the opposite. In fact, the research team led by Jan Ambjorn and Yoshiyuki Wadabiki came to the conclusion in their study that it was the fusion with another cosmos that paved the way for our universe in the first place. Basically, we must not forget one thing. The accelerated expansion of the universe still embodies one of the greatest research mysteries of our time. Let's just take a look at the confusing deviations in the Hubble constant, which indicates the rate at which the universe is currently expanding. If we determine the corresponding value using the cosmic background radiation, we obtain the Hubble constant of 67 kilometers per second per megaparsec. However, as soon as the expansion rate is determined using supernovae, red giants, gravitational lensing, and variable stars, the Hubble constant is suddenly 73 kilometers per second per megaparsec. The puzzling discrepancy that means nothing other than that the universe today is expanding faster than it should be, and which was recently confirmed once again by the James Webb telescope. In order to check the datasets of the past for any errors, Webb took a look at over 320 variable stars, so-called Cepheids, and on this basis provided proof that the impossible deviations are indeed real. However, the background to this fact is just as uncertain as the answer to the question of what is behind the accelerated expansion of the universe. In order to explain the cosmic speed boost and reconcile it with the standard cosmological model, experts have postulated a mysterious force that counteracts gravity, dark energy. However, this hypothetical form of energy has not yet been directly proven, and so far, it has only been recognized on paper by the fact that it boosts the accelerated expansion of space. And so it is that some astrophysicists sometimes seriously question the actual existence of dark energy, and instead look for alternatives to explain the processes in the universe. However, the aforementioned study by Ambjorn and Wadabiki provides that these alternatives can also be very surprising. Published in the Journal of Cosmology and Astroparticle Physics, it comes to the conclusion that the expansion of the cosmos could in fact be driven by the constant merging with other universes. What's more, according to Ambjorn, merging with the so-called baby universes is even able to explain the collected data better than the standard cosmological model. In principle, the hypothesis that several universes interact with ours is not new. But what is new is the mathematical model that the experts used in their study to investigate the possible effects that such a scenario could have on our world. The researchers' calculations showed that merging with other universes could increase the volume of our own, an effect that could be perceived by our instruments as cosmic expansion. In addition, the scientists also determined the rate of expansion of the universe that would occur in this case, and realized that their results are ultimately more consistent with actual observations in space than the traditional standard cosmological model. Furthermore, the authors also addressed the problem of cosmological inflation in their study, and in doing so, broke away from the idea of the aforementioned inflaton field. Instead, the scientists explained the super-fast expansion of the early cosmos by the fact that our young universe was absorbed by a larger parent universe. Following on from this, the experts hypothesized that our universe continued to collide with other baby universes after its own absorption, swallowing them up as well. To test their groundbreaking theory, the experts are currently conducting a series of experiments to uncover the hidden properties of the microwave background. Ultimately, however, the future will have to show whether the established standard model or the baby universe theory is better suited to describing the current expansion of the universe. Yoshiyuki Watabiki is pinning his hopes entirely on the data that the James Webb and Euclid telescopes will collect in the future. And we are now pinning all our hopes on the new subscription that you will hopefully be collecting. Feel free to press the thumbs up and subscribe now to never miss a new video from us again.